All right. To build upon what we were just talking about, or what I recently lectured on, was building a peptide from individual amino acids. Now, that is foundational to a discussion of proteins because amino acids are the building blocks of peptides. Amino acids are also the building blocks of proteins. Now, the difference between them is that generally, a peptide is anything, or a polypeptide, anything up to 50 amino acids is going to be referred to as a polypeptide, whereas anything above is going to be referred to as a protein. Now, the structure of proteins is of extremely great interest because you're kind of operating on the idea of what something looks like, you know how it interacts within space, then you can get a sense for, well, how it behaves in other settings, and how it responds to certain stimuli, and to certain molecules. For instance, if you know a protein looks a certain way, then maybe you could design a molecule that binds to a specific pocket in that molecule, into that protein, and maybe like restricts its movement, restricts its ability to catalyze a reaction. So, unlike most organic polymers, protein molecules adapt a very specific three-dimensional conformation. So, whenever I say three-dimensional conformation, this conformation is basically another way of saying fold or shape. Tablet, did it do it again? So basically, what does that thing look like? That's the question in conformation. Now, this structure is able to fulfill a specific biological function. So what that thing kind of folds itself into is going to help it do a specific job. Now, that shape that protein adopts is commonly referred to as the native fold. The native fold or shape has a large number of favorable interactions within that protein that you can think about them as stabilizing them. And one thing I want you to keep in mind throughout this discussion of protein structure is we're talking about a polymer of amino acids. So this large number of favorable interactions, those are your amino acid R groups that are interacting with one another. For instance, if you think about a lysine residue, lysine is a positively charged polar amino acid. Lysine is an amino acid that's going to like to form a favorable interaction with an amino acid like aspartic acid, for instance. Aspartic acid is a negatively charged polar amino acid. But one other factor you got to think about, that hydrophobic effect, where these non-polar molecules kind of aggregate together because they want to be away from water. Now, there's an entropy cost of folding of a protein into one specific fold, into one specific shape. So I just kind of alluded to specific favorable interactions in proteins, but in a more general sense, what are some favorable interactions within proteins? You've got the hydrophobic effect, where you're going to basically have groups that get together, and in the process, they're going to force water away from them. And whenever you have that take place, sorry about that. So you have these groups that are non-polar, that they're going to want to be in close proximity to one another, and they're going to force water out, and that's going to lead to an increase in the overall entropy of that system. Another favorable interaction, and sorry, whenever we think about this hydrophobic effect, I think it's important to think about the individual amino acids that could participate in this. So as an example, a non-polar amino acid would be something like valine or isoleucine. If you have a high concentration within a protein sequence of valines and isoleucines, well, then those are going to probably interact with one another because they're all residues that are non-polar. Now, you also have a large number of hydrogen bonds. You have interactions of the N-termini and C or carbonyl groups of the peptide bond that lead to local regular structures such as alpha helices and beta sheets. And we're going to talk about those in just a little while. You also have your weaker interactions, your London dispersion forces, these mid-range weak attractions between all atoms that contribute significantly to the stability of the interior of the protein. Now, what I think is really important to think about with respect to protein structure is you have strong interactions, you're going to have some covalent interactions. Mostly, though, you've got non-covalent interactions, and you don't even really have like exciting, or it's not even a matter of you've got tons and tons of ionic interactions. You've got weak non-covalent interactions. You've got like London dispersion forces. You have hydrophobic interactions that are going to create a kind of a groundswell or a large number of them that are going to stabilize the 3D structure of that protein. You've got these electrostatic interactions, long range, strong interactions between permanently charged groups. I kind of alluded to those with your lysine and arginine as both positive groups, and then aspartic acid as a negatively charged group. And so you'll have those that help stabilize the protein's overall structure. Okay, now when we talk about protein structure, we have a total of 4 levels of protein structure. If you look on the right-hand side of this slide, you're going to see the quaternary structure, and you're going to see the tertiary structure. Now, that is something that has your 3-dimensional fold. But where does that come from? Well, that comes from the primary structure. Your primary structure of a protein is going to be just basically the sequence of that protein, starting with that N-terminal or N-termini, going all the way to the C-termini. I showed that I shared with you all the primary structure of that dipeptide DS, where we had the aspartic acid that was followed by the serine. This primary structure is read in the N to C direction. So starting with your N-terminal amino acid, what's that identity? And then what's the next amino acid's identity? All the way till what is the C-terminal amino acid and what's that identity? Now, the primary structure is going to be stabilized exclusively by covalent interactions. So those covalent interactions are simply going to be the peptide bond that holds together that amino acid backbone. So covalent interactions stabilize the primary structure. Now your secondary structure. These are somewhat commonly referred to also as local structures, because what we have here is we have kind of amino acids that are in close proximity to one another. They're going to kind of interact and contort themselves, and they're going to move this entire structure in a specific way so that we get to what is this region of the primary structure look like when it's folded in 3D. Now, your secondary structure is going to be stabilized, and this is hierarchy. This is a hierarchy. So if the primary structure is stabilized by covalent bonds, then the secondary structure is kind of building off of the primary structure. But what we want to know is what are the interactions that stabilize that secondary structure, that stabilize this, what's known as an alpha helix? And the answer to that is you have hydrogen bonds. You have backbone hydrogen bonds. So what are the atoms within a peptide bond that interact with other atoms within a peptide bond? So your secondary structure is stabilized by backbone hydrogen bonds. Your tertiary structure, well, this is kind of interesting. Your tertiary structure, if you look at this alpha helix, oh, I didn't mean to zoom in there. This alpha helix right here, that's this alpha helix right here. And it's almost like the tertiary structure gives the secondary structure a little bit more context. You can see which amino acids or which local structures are formed and where are they. Now, what stabilizes the tertiary structure? Well, the stabilization of the tertiary structure is largely going to be through side chain interactions. So what does that R group look like? So that's where you're going to have things like, you know, a serine interacting with, say, an asparagine. You have 2 polar groups that they're capable of hydrogen bonding. You might also have a salt bridge or something like that. So maybe something like a an arginine interacting with an aspartic acid. And then you might also have something as wild as like an aspartic acid interacting with a sodium ion, which interacts with another aspartic acid. So your tertiary structure is largely R group interactions. And whatever an R group is capable of, then the tertiary structure is capable of that. Now, with that in mind, that's largely going to be hydrogen bonds. You might have some ionic interactions. There's one amino acid, cysteine, which is capable of forming a disulfide bond, which a disulfide bond is an example of a covalent interaction. So your tertiary structure is, to put it simply though, or to simply put the tertiary structure and what it's stabilized by, R group interactions, how the different R groups of this polypeptide interact with one another. Now this next level, this highest level here, this quaternary structure. The quaternary structure, if you look at the bottom, it says assembled subunits. So what that means is that you have a protein that has multiple different subunits. These different components, these individual polypeptides, they are subject to their own primary, secondary, and tertiary structure. They're going to fold in a specific way. But then that polypeptide, which folds in a certain way, is going to interact with another polypeptide. These are two independent polypeptides, but they're going to interact with one another, and they are going to form something that has its own shape. So its own three-dimensional structure, its own fold. I apologize. I always like to think about, this right here is an example of a primary structure from the N termini to the C termini. And then if I zoomed in, okay, well, there's a little loop-de-loo. That's a secondary structure. This would be a tertiary structure. Then I'm going to get another polypeptide, a little hair bun thing. This right here, where I have two polypeptides that fold together to make a quaternary structure. Now, what's kind of complicated about the quaternary structure is, a very good question is, well, what types of interactions, bonds, what's going to stabilize a quaternary structure? Well, I previously said that the quaternary structure is made up of individual tertiary structures. Well, you have R groups on one polypeptide and another polypeptide that will interact with one another. And so those groups are going to be in proximity to one another. They're going to form a structure. And so it's going to be R group interactions again, but it's R groups on different polypeptide chains. So that's the key difference between the tertiary structure and the quaternary structure. The tertiary structure is one singular polypeptide. The quaternary structure is at least two polypeptides that have folded together to make one complex shape. Now, the types of interactions that stabilize the tertiary and quaternary structure are largely going to be the same, but it's all about, is it a single peptide or is it multiple peptides? Now, with that in mind, not all proteins have a quaternary structure, because not all proteins are going to fold and interact with a second polypeptide or a third polypeptide. Now, this protein right here, this is what we're looking at here is hemoglobin. Hemoglobin is a tetramer. It has 4 individual subunits. And we'll talk about hemoglobin a bit more whenever we're talking about protein structure or higher level protein structure. So there's a quaternary structure. Okay, so just to recap, primary structure, covalent bonds stabilize it. Secondary structure, backbone hydrogen bond interactions stabilize them. Tertiary structure, R group interactions. So ionic interactions, hydrogen bonds, hydrophobic interactions, covalent bonds in the case of cysteine forming disulfide bond. Quaternary structure. Anything that is stabilized is the tertiary structure, but between different polypeptides is going to stabilize the quaternary structure. Okay, now the primary structure. The structure of protein is partially dictated by the properties of the peptide bond. The peptide bond is a resonance hybrid of two canonical structures. The resonance causes the peptide bonds to be less reactive, hence why we're not going to see a positive charge or an overall charge on those peptide bonds. If we compare that, they're going to be quite rigid and nearly planar. That's why I said you have those 4 atoms within that peptide bond in the same plane. To exhibit a large dipole moment in the favored trans configuration, we've got something that looks like this. So on the far left-hand side, I would say that's the most commonly displayed way that you're going to see a peptide bond. You've got just a second, I got to get my pen function back. These are, and I would say that this is a pretty comfortable, these are the 4 atoms that constitute a peptide bond. Some people will include those 2 alpha carbons, so you've got 6 atoms that constitute a peptide bond, but we've got stabilization where we're going to have a carbocation, which carbon generally doesn't form a cation. And so, sorry, that's why we have that double bonded oxygen there on that carbon. So this essentially is the summary of the peptide bond and the kind of building block for a primary structure of a protein. Okay, so we're going to dive in this quite a bit more in just a little while because we're going to ultimately get to secondary structure, and that's where we're going to stop for this first exam. And that's where I'm going to stop this video. So hang on, we're going to talk about secondary structure in just a minute.